Okay guys, last time we were talking about congruence. Let me just continue with the sequence. So that was congruence of the sequence basically. You don't need to write it down again because I actually talked about it. So what we have is a sequence here. Let me just set this here. So congruence of a sequence. So if you can't read this, I can't read it either. As I said, get it to sometimes it's crazy. So, okay. So congruence of a sequence. Okay, so maybe you remember, guys, the formal definition was for all positive numbers, okay, there is actually a, let's say, natural number that I call capital M, for which we have that the distance between the following members of the sequence and A is, which is the limit, okay, is less than epsilon, okay, so for all capital N, so for all n greater than equal to capital N, if you like, okay. So that means that the sequence, okay, so this is the sequence here, okay, so that's the sequence, and of course that is the limit, okay. So in that case, no matter how small this distance epsilon is, to which actually, I mean, I'm talking about the distance between the members of the sequence of the limit, no matter how small that might be, actually there is always a member, so you can always find a member with the index, let's call it capital N, alright, so this is the index capital N of the member, from which actually all following members have a distance to the limit which is strictly less than that, okay, so even that, this means that actually the sequence AN can get arbitrarily close, okay, can get arbitrarily close to the limit, okay, this is the limit A, okay, so the limit is actually A, alright, so that was what we're talking about last time, and actually that I was stating here that the limit of a sequence, if it exists, okay, so the limit of a convoluted sequence is always unique, so that was actually the last statement that I would actually try to prove, but I ran out of time, or actually basically I ran out of battery, maybe remember that, so this is the theme, so the limit of a convoluted sequence of a convoluted sequence is always unique, okay? So if the limit exists, right, so if the sequence is convoluted, then it cannot have two different limits, okay? So basically, that is a statement that I would like you to prove here. Okay, so the limit of a convoluted sequence is unique, and convolence means that the sequence can get arbitrarily close to its limit. Okay, if the limit exists, it can get arbitrarily close to it. So this is what we were talking about. Now, okay, so let me prove this. Okay, so suppose that we have, so if, let's say, in that case, suppose that AN, okay, so the sequence converges to A, and also it converges to A prime, and that A is not equal to A prime, so which means that the sequence has two different limits, okay? Alright? So in that case, so, and if that's the case, then I will show you that this is a contradiction, okay? So this is actually what the proof is about, because if there is a limit, then it must be unique at all times, okay? So this is actually what we have here, and now the thing is this, and we select, I mean, we can select anything we like, okay, so what we do is we select the distance between the two limits, okay, so we assume that actually that epsilon, the distance, okay, so that we choose is basically the distance between the two limits, or actually to be precise, it is half as large as the distance between the two limits. Okay, so if the two limits don't, if these two limits are not equal, then this expression is always greater than 0 because the limits are not equal. So we choose epsilon to be the distance we choose, is actually that half as large as the limit, half as large as the distance between the two existing limits, okay, that supposed to exist if the limit is not unique. Now guys, okay, so in this case, this is the distance that we choose, and I'm going to show you that this is a contradiction. So now, therefore, this means that there exists, okay, so in that case, then there exists two natural numbers, okay? In the most cases, these two natural numbers are different, but they can be equal as well. So the first one is capital N, and the second one is N prime, and they're all natural numbers, okay? So from which actually the distance of the members of the sequence and the corresponding limit is always less than epsilon, okay? Such that, okay, so in that case, so such that on the first hand we have that the distance of the sequence between the limit A is less than epsilon, and we also have that the distance of the sequence and A prime is also less than epsilon, okay? So, and this, in that case, so for all, okay, for all n being larger than equal to the maximum of the two natural numbers, okay, let me just add this here, all right, so for all n that is larger than the maximum of these two indices, okay? So why I'm using the maximum here, guys? Okay, just let me answer the question. Maybe you can copy that first, and then I'm going to actually answer that, okay? Okay, so this is actually a statement that I can make in that case, all right? So there is actually a member of the first sequence, and there is a member actually, another member that might be another member here, from which all following members have a distance which is strictly less than epsilon, okay? So why I call it's actually the maximum of capital N and the N prime? And the reason for that is, okay, I apologize. This is like, anyway, you cannot adjust as you want to. It has to be always like as the machine wants. Anyway, okay, I did talk about last time. So now, suppose guys that we choose, I mean the distance is relatively small, and suppose that here in this case, after the 10th member, okay, of the sequence, okay, so from the 11th member on, actually the distances are less than, the distance between the members and the limit is less than epsilon, okay? And here, suppose that for this case, for this limit here, the distances are less than that, let's say from the 11th member, okay? So here we have the 10th member, and if we have the 11th member from this equation, that is true. Now, if we take the 11th member, then this equation and this inequality might be both true for both of them, okay? So if you take the largest of the two, n and n prime, then all following members, no matter how large the maximum is, will have a distance that is strictly less than epsilon to both limits, okay? So to both of them, namely epsilon, here A and A prime, okay? So if the sequence has two limits, and then we select certain members from which actually the members have a distance which is strictly less than epsilon for both of them, and we take the maximum, so in that case, of the maximum of that index of the member, that we have that actually that both inequalities hold, because both distances to the members of A and the limit A and A prime will be strictly less than epsilon, okay? So from the maximum of the two, okay? So if these two natural numbers would not exist, okay, then the sequence would not have actually, I mean, if these two numbers did not exist, okay, sorry to be precise, then the sequence would not have two different limits, okay? Now, guys, and let me just move on, okay? So in this case, for that we see the following inequality, okay? So here in this case we have the following. So we have the 2 times epsilon, okay? So from this equation here, okay? So 2 times epsilon will be equal to the distance of the two limits. That is obvious, okay? Now here, the distance of the two limits, maybe you remember the triangle inequality, okay? So because the absolute value satisfies the triangle inequality, because that is, of course, let's say a metric, remember that in the first dimension. So in this case, I mean, we'll talk about that. So this inequality holds, okay? So this is being less than equal to the distance of A and the limit, okay? So A and basically A and the, or A minus AN, okay, plus, and then here we have that this is A prime minus AN, or AN minus A prime to be precise, okay? So this is actually true from the viewpoint of the triangle inequality, okay? So this is, this inequality is actually, this inequality holds, okay? So due to the triangle inequality. Maybe you may remember that. Okay? The absolute value satisfies that. Okay? So the distance between these 2 points is not greater than the sum of these two distances. Okay? So where actually AN is the arbitrary point for which actually all sequences have strictly the distance for them is strictly less than that of epsilon. Now in this case we have that this thing here, that one, okay, so the first one is strictly less than epsilon, and that is also true for the second one, okay. Maybe I can add this here, okay, so I shift that a little bit away, and so we have that this is strictly less than epsilon here due to the first statement, okay, and we have that this is strictly less than epsilon as well due to the second statement here that we figured out. Okay, so now in this case we have that this sum is must be strictly less than epsilon. Okay, so or basically strictly less than 2 times epsilon to be precise. Okay, so because we have the first one, okay, and then we have that from the second statement, okay, which is 2 times epsilon. Now, here we figured out, guys, I mean, just have a look at that. That, I mean, if, let's say, the limit has, if the sequence has 2 different limits, then we would have that 2 times epsilon is strictly less than 2 times epsilon, which is a contradiction. Okay? So this cannot be, right? Okay? So because 2 times epsilon is not strictly less than 2 times epsilon. 2 times epsilon is always equal to 2 times epsilon. Okay? So this is a contradiction. Okay? So which, all right, so to conclude, this is a contradiction. So hence a sequence cannot have 2 different limits. Have, okay, cannot have 2 different limits. All right? So this is the proof of the statement. Okay, so if the limit exists, then we have that actually, that and it is always a thing. All right? Okay, so then we have the following remarks here to that, because that remark which we have here is also true for all the congruences, no matter what. I mean, we're looking at different types of congruence here in this context, so that would be also true no matter what. So here, for instance, we have that, let's say that we have a sequence A, and the limit of the sequence A as the sequence progresses, okay? As a sequence progresses, let's say, is equal to A, okay, and the limit of the sequence Bn shall be equal to B, okay? So we have that we have 2 different sequences, An and Bn, okay, and both of course can have different limits. I mean, the limits here do not have to be equal, of course. Okay, so then we have the following properties. Okay, so the first property of the limit is the additivity property. So additivity means that the sum of the limits is equal to the limit of the sum. So Okay, so we have that basically, in this case, so the limit of an plus bn, so the limit of the sum of the two sequences will be equal to the sum of the limits. This is the additivity property. Okay, so if the sequence B converges to B, and if the sequence A converges to A, then the sum of the two will converge to A plus B as the sequence progresses. Okay, so and that property is called additivity property. Okay, now second we have the homogeneity. Okay, so we say that the limit is additive. Okay, so if let's say some guys make the statement that the limit is additive, then it's just that. Okay, and we also have the homogeneity of the limits. I mean, this is actually true for both of them. So we have that, for instance, limit of k times sequence A equals, okay, so this will be k times an, sorry, k times A if A is the limit of the sequence. Okay, so if I, let's say, do the following, if I multiply all members of the sequence by 5, okay, then the limit of the sequence, if it exists, will be also multiplied by 5. Okay, so that's the homogeneity property of the two. Okay, so in this case, if let's say a certain operator, let's say the limit, is both additive and homogeneous, then we call it linearity. Okay, so the linearity property, this is not in the lecture notes, guys, but I would like you to add this here. So the linearity means that it is additive and homogeneous. Okay, so this means that additivity and homogeneity. All right, so it is both additive and homogeneous, and in this case we call it linear. Okay, so linearity means exactly that. Okay, so the limit of the sum equals the sum of the limits. Okay, and we have, let's say, the limit of k times the sequence equals k times the limit of the sequence. Okay, a certain factor, so k is actually an arbitrary number. Okay, you understand that? Now, we also have that the limit is also multiplicative. Okay, now in this case, I mean, this is also important, but this is not always true for all other operators in a linear. For instance, if you remember the differential operator, okay, or the derivative. Okay, so we have the derivative is actually linear because it's both additive and homogeneous. The sum of derivatives, the derivative of sum equals the sum of derivatives, and the derivative of k times a function equals k times the derivative of the function. So the differential operator is actually both additive and homogeneous, but it is not multiplicative, and that's but the limit is. So in this case, so we have that multiplicativity. Okay. So the multiplicativity property means that in this case, even the limit of the product, okay, of the two will equal to the product of the limits. Okay. Now there are also other properties that I'm not going to discuss here, but these are actually the most important ones. Okay. And now I would like to talk about the so-called Cauchy sequence. Okay. In the following parts from definition 5.5 to 5.9, I'll discuss actually the so-called geometric series. Okay, so maybe you can look at that. So what the geometric series is and how actually a series converges and stuff like that. So we can, you should look at that. So, but I'm not going to discuss it here because this is something that you have seen also in, probably you're supposed to see in mathematics as well. So I'm not going to discuss that. Okay, so definition. From definition 5.5 to 5. Let's say 5.8. Okay, so we mark. Okay, so definition 5.5 until the mark. We have 5.8. We have series. Okay, and we have the so-called geometric series. I'm going to skip that here in this lecture because that's not that important for us. Okay, so from definition 5.5 to 5.8, we have the definition of series, and as an example, I take the limit of geometric series, if it exists. Okay, but I'm not going to discuss it here. I skip that here. Okay, you will need this in finance and certain calculations, but it's too easy. Okay, so this is actually what the limit is about. As I said, most important properties are the limit is unique, the limit is additive, the limit is actually homogeneous, and the limit is multiplicative, and that's it. Okay, so these are the most important ones, as I said before. Okay, there are also different ones, but I'm not going to discuss them here due to we have not so much time. Okay, now guys, I'm going to define a so-called Cauchy sequence. Okay, so this is going to be the next definition. This is going to be definition 5.9. Okay, so what is actually a Cauchy sequence? Okay, sorry, I missed a U here in between. Okay, so Cauchy sequence. Yes, Cauchy Sequence inequality, right? That's something like that. You heard of that too. Okay, guys. Now, what is a Cauchy sequence? A Cauchy sequence is actually a sequence where the members can get arbitrarily close, not to a limit, but to each other. Okay? Alright, so here in this case, and this is the implementation, okay, so the members of the sequence can get arbitrarily close to each other. Okay? Let me just summarize that. So the members of a sequence, of a Cauchy sequence, okay? Cauchy sequence can get arbitrarily close to each other, okay? Okay? So they can get arbitrarily close to each other as the sequence progresses. And now how do I express the formula? Okay, so in both cases, I mean, this is relatively easy. So here for all positive distances, let's say, okay, so epsilon is an arbitrarily small distance, okay? There is, okay, let's say there is a natural number. So basically it's quite similar. That satisfies the following property. Okay, so the natural numbers satisfy the following properties I'm talking about here. So I'm taking two members of the sequence, so an and am, all right, and I subtract the two from each other. Okay, and the distance of these members, okay, will be strictly less than epsilon from the index capital N on. Okay, so here in this case, so I'm taking the index capital N, and what I find is that the distances, the following distances of two members, any members that, you know, the sequence has, will become strictly less than epsilon, so which is strictly less than the chosen distance. Okay, so for all, so what we have that for all N and M which are greater than or equal to capital M. You understand that? Okay? So no, this means the following. I mean, let me just illustrate this. So no matter how small you might choose a distance, okay? So I'm talking about epsilon here. So no matter how small epsilon, which will be the distance here, is, okay? So let's say it's 1/2 billion or something, okay? In case of a Cauchy sequence, okay? So this is what we're looking at. The distances of all following members to each other, okay? So I'm talking about the distances of the members with respect to each other, okay? Will be always less than that after a certain point. So after a certain point, no matter where it is, okay? So suppose it's somewhere in the sequence. All distances of all members, all following members to each other, no matter what kind of members you take, will be strictly less than that. So that means that the members, okay, so the following members will get arbitrarily close to each other. You understand that concept, okay? And that is a Cauchy sequence. Now there is a difference between a convex sequence and a Cauchy sequence, okay? So in this case, just because we have a Cauchy sequence, it doesn't mean that the sequence is convex. So let's say, for instance, as an example, I had this before and I talked about it. So suppose that an is actually a sequence of the rational numbers, and an is defined as follows. So this will be actually 1 plus 1 over n to the power of n. Okay, so you already recognize that the limit of this sequence will be the orderless number, but the orderless number is not a rational number, so this sequence an does not have a limit. Okay, a limit in Q. Okay, so there is no limit of the sequence in Q because that tends to a irrational number. Okay, so the sequence has a limit, which means that the sequence does not converge. Okay, so the sequence does not converge because it has no limit in Q. Okay, so we define this as a sequence of rational numbers. Okay, not a sequence as, you know, as real numbers. Okay, so in this case, so this sequence does not converge. Okay, so hence, an does not converge, let's say, in Q, so it doesn't have actually a limit there, but it is a Cauchy sequence, so this is something that you can show that the members can get still arbitrarily close to each other even the sequence does not converge. Okay? Do you understand? Okay? So, but it is a Cauchy sequence. Okay? So, but an is a Cauchy sequence. I'm not going to show that. That is relatively easy. Okay? Because the members can get arbitrarily close to each other. Okay? The members can get arbitrarily. Okay? Okay, sorry. Close to each other. Okay. All right. Okay, so this is an example of a sequence that does not have a limit, but it's a Cauchy sequence. Okay. So just because the members can get arbitrarily close to each other, it doesn't mean it converges. Okay. So the opposite is true. So if the sequence converges, then the members can get arbitrarily close to each other, which means that if it converges, then it is a Cauchy sequence. Okay. And that is something that we can actually summarize here. Okay. So if a sequence converges, then it's a Cauchy sequence. Okay, so this is a remark that I would like to make here. So if a sequence converges, then the sequence is a Cauchy sequence. Okay. So if an is convoluted, then it is a Cauchy sequence. Okay, but no, please note that the opposite is not true in general. Okay, so if they can get arbitrarily close to each other, the members, then they, if they can get close to arbitrarily close to the limit, then they can get also arbitrarily close to each other. Okay, so the proof here is actually of theory. So the proof of theory 5.11, which is relatively similar to the proof of the uniqueness of the limit, so I'm going to skip that here. Okay, so we already have seen something which is quite similar than that, so if you want to look at that up, you can check it out. It's not difficult at all. Okay? But please note that actually get the other direction, so the conversion is not true in general. Now, you can see that actually something incompleteness here regards the set of rational numbers here. I'm talking about the set of rational numbers. Okay? So what kind of incompleteness is that? Okay? I mean, just suppose that if, let's say, this was the limit of that sequence, which exists over the set of real numbers, was a rational number, then the limit here would exist. So that means that somehow the sequence or the set here, Q, is not complete. You understand that? Because not all Cauchy sequences have their limits. You understand? Okay? So a set is actually, let me just define this. Okay, so we were, this is going to be in definition 5.15. Okay, so a set, okay, so definition. So a set omega is called complete. Okay, so we're talking about complete sets. If every Cauchy sequence converges in omega. Okay, you understand that? Okay, so if you have a Cauchy sequence and it converges, and all Cauchy sequence in that set converges, in the set, then we call the set complete. Okay, obviously we have that, and this is what we have. Okay, so that Q is not complete. Okay, as we've seen that here before, so the reason was, for instance, an. Okay, so 1 plus 1 over n to the power of n is a Cauchy sequence. So this is an example, but it has no limit in Q. Okay, so we already talked about it. Okay, so this is actually what I have demonstrated in this case. Okay, so if the set was complete, then actually that all Cauchy sequences would have a limit in there. This is not the case. Okay? All right, does it make sense? Now, let me just come back to the equivalence relations, because equivalence relations are actually important, guys. Okay, so let me just define an equivalence relation. So I'm gonna use that as an example. So let's say we have two Cauchy sequences. Okay, so let an and bn denote two Cauchy sequences, and then I'm going to find a relation over the set of all Cauchy sequences over a certain set. Okay, so then check it out. So let's say an, okay, so the sequence an relates to the sequence bn. Okay, remember? If and only if, remember that? Okay, so the relation, if and only if, let's say the limit of the difference of the two, okay, as the sequence, or as both sequences progress, is equal to 0. Okay, so we have two Cauchy sequences, and here in this case, let's say we have that the limit of the difference of the two Cauchy sequence is 0. Okay, so in that case, then they relate to each other. You understand? Now this relation is, of course, reflexive, symmetric, and transitive. Remember? Okay, why is that? Now let's go through this. So this relation is, of course, reflexive. Okay, because an minus an, as always, the sequence does always converge to 0. So the difference of the sequence to itself is always congruent, and the limit is always 0. I mean, this is obvious. This is bloody obvious because all members are equal to 0, right? Okay, so if all members are equal to 0, then the limit of the sequence is 0. That's bloody obvious. Now, guys, the sequence, I mean, the relation is also symmetric. Why is that? Because if the limit, let's say, of an minus bn converge to 0, so if the limit converges to 0 of the difference, then the difference of bn minus an will also converge to 0. Okay? So that is also obvious, and of course the transitivity property is also true, because let's say if the difference of an and bn converges to 0, and the difference of bn and cn, let's say the third one, is also converging to 0, then the difference of an and cn must also converge to 0. Okay? That is also obvious. Okay, so in that case, I mean, this relation is an equivalence relation. Okay, so the relation, okay, so the relation defined here above is an equivalence relation. So this is an equivalence relation over the set of all Cauchy sequences. Okay? And now I'm going to define what the real number is. And this is, you have, maybe you remember the equivalence relations, right? So the equivalence relations generate what? They generate an equivalence class. You know what I'm saying? Okay? So then, for instance, they generate this equivalence class. So then, for instance, the real number, and then, so we can define the real number, and this is going to be the following definition. Okay, so a real number is an equivalence class of Cauchy sequences of rational numbers generated by relation. Okay, so of Cauchy sequences of rational numbers. Okay, so here generated by the, okay, so generated by the equivalence relation of the example above. Okay, so we talked about it. So we can define equivalence relation as a difference of two Cauchy sequences where the limit of the difference is equal to 0. So in that case, and this is an equivalence relation, so it generates equivalence classes. Okay, and equivalence classes are real numbers. Okay, and the real number is actually an equivalence class. So the set of all equivalence classes will be actually the set of real numbers here in this case. Okay. All right, so that is what the real number we have here. Okay, so this is, and this definition is from Dedekind in the beginning of the 20th century. Okay, so that was actually the solution how we define real numbers properly. Okay, so you can look it up. Okay, so this is the definition of Dedekind. Okay, I think in the beginning of the 20th century. Okay. Now, guys, of course, we talked about that the set of rational numbers is not complete. So here, I'm going to add this as a remark. Okay. So the set of real numbers, namely the set of all equivalence classes generated by these Cauchy sequences on the equivalence relation of Cauchy sequences that I talked about previously, the set of real numbers is complete. Okay. Okay, which means that all Cauchy sequences, okay, in that set have a limit in the set of real numbers. Okay, so that is actually how you achieve completeness. Okay, so we extend the rational numbers, okay, by using this way. Okay, so using Cauchy sequences. So we take actually all Cauchy sequences that are defined in the set of rational numbers, and we generate the limits. Okay, and we add these limits to the set of rational numbers to get the real numbers. Okay, so that is actually how you define the set of real numbers. All right. Okay. This guy was actually a genius. Okay, so basically, I mean, of course we don't prove that. So the property, and we would have gone through the property of fields, etc., but we don't do that. So we skip that. This is very important. Okay. So in this case, since R is complete, so this means that actually a sequence. Okay, so a sequence in the set of real numbers is conjugate if and only if it is a Cauchy sequence. Okay? And that is also true for any other complete sets, okay? So within a complete set, okay, so suppose that the set is complete, then a sequence is any sequence on the set is conjugate if and only if it is a Cauchy sequence. Okay, so if it's a Cauchy sequence, then it would be conjugate. So if the members can get arbitrarily close to each other, then they can also get arbitrarily close to a certain limit. And if the members of the sequence can get arbitrarily close to a certain limit, then they can get arbitrarily close to each other as well. So this is equivalent in that case. Okay, so that's why actually we call it equivalence relation. Remember that. Okay, so maybe now it's clear. Okay, because the two here in this case are equivalent. All right. Okay. But this is only true for a set that is complete. Okay, so if the set is not complete, then only the first direction is true. So if it's conjugate, then it's a Cauchy sequence. But just because it's a Cauchy sequence, it's not necessarily conjugate. Okay, so provided on which the sequence is defined on. All right. Is this something that is clear, guys? Okay. So we will look at. I mean, there will be some statements regarding this in the assignments, but you'll find everything in the lecture notes. Okay, so this is on page 21 and 22. Okay, so if you get confused, then you have the examples and you find everything in that as well. Okay, now let me just consider the next limit. Okay, so this will be the so-called limit of the function. Okay, so I'm gonna define this later on. So here we have the following. Okay, so now let's define it now. So this is the definition. So that's number 3. Okay, so we talked about the limit of a sequence, and we talked about what a Cauchy sequence is, and then we talked about what the limit of the function is. Okay, so what is the limit of the function? Okay, so let me just illustrate that first, and then you can check it out later. Okay, so what we have is suppose that we have xn, and xn is a sequence that converges to, let's say, to a certain value p. Okay. All right. Okay. So in that case, okay. So if, let's say, in that case, so if a certain function, okay, so the function of the members converges to, let's say, to L, then L is said to be the limit of the function. Okay, so this is what the limit of the function is. Okay, basically there is a definition which is more abstract than that. Okay, but it's not really intuitive. So basically you don't need to consider that. So what we have is actually the following. So basically, if let's say xn converges to p, then this implies that, let's say, f of xn converges to a certain limit. Let's call it L. Okay, so L will be the limit of the function if that statement is true. Okay, so from the convergence of the sequence, so that means that the images of the sequence. So if, let's say, the sequence converges to p as a sequence progresses, then the image or the images of the sequence converge to a certain value, and if that's being the case, then the sequence is called, or let's say the function is, or capital N will be called the limit of the function. Okay, you understand that? Okay, so there is actually a more abstract definition of that, but we already know what the sequence is, and we already know what the convergence of the sequence is. So by using that, we can also define the convergence of the function, or the limit of the function, let's say, without looking at the abstract definition of the limit of functions. Okay, you understand that? So let's say if the statement is true that this implies, okay, so this implies that statement, then the limit, so then L will be the limit of the function. Okay, that's it. And that is enough because we already know what the convergent sequence is. Okay, so suppose that we have a convergent sequence, and if the image or the images of the members will also converge, then we have the limit of the function. That's it. Okay, and that must be true for all sequences. Okay, so for all, let's say for all xn, so for all sequences. So that statement must be also true. So there It's not allowed to have an exception to that. Okay? So that must be true. You understand that point? Okay? That is actually, I mean, that was actually what we're looking at. So this is something that you already know, for instance, from the, let's say, from the following example, just to have the relation to that. So for instance, let's say you have the limit of, let's say, x squared minus 4 over x plus 2 as x approaches negative 2. So as x approaches negative 2, so you have 0 in the denominator. So if you have 0 in the denominator, then of course the expression is not defined, remember. Okay, so this is what the limit of the function is at that point, you understand? Okay? And of course, x squared minus 4 equals, so here you have that this is equal to x minus 2 times x plus 2, right? Okay? I don't have any space, so I'll continue here at the bottom. Okay, so this is going to be equal to the limit of x minus 2 times x plus 2 over x plus 2, which means that x plus 2 cancels out. Okay, so here I have the limit as x approaches negative 2. So here we have that this is going to be the limit of x minus 2 as x approaches negative 2. So as x approaches negative 2, then x minus 2 approaches negative 4. Okay, so this is the limit of the function. Okay, you understand? Okay, so just let me summarize that, guys. Okay, I'll wait for you just to write it down. Okay.
Sorry, why
yeah.
should x go to minus 2 and not 2?
Because we want to check out what happens with the expression as x approaches negative 2. Okay? Because the denominator, look, the denominator, the point is that the denominator here, okay, so the denominator will actually approach 0. But although the denominator approaches 0, the expression is actually finite. That's the thing.
Okay, so if x goes to 2, then it would be
negative 2.
Yeah, but if it would go to 2,
then the limit is 0, obviously.
Yeah,
okay? Because you have something finite in the denominator which is strictly greater than 2. Okay, so that is not interesting here in that case, and the limit will be 0. Okay? But that's not very interesting. I mean, this is something that you have already seen, but you were not aware that this was defined actually just in terms of the limit of the function. Okay, so if I know what the convoluted sequence is, then I can actually define what the limit of the function is by using that. Okay, so basically, I mean, this example was as follows. Okay, so here I have xm was, let's say this was, I mean, you can define this as follows. So, or xm, let me just say. Okay, so xm was converging towards 2. Okay, so it tends to 2. Okay, so in that case, this implied that x n to the power of 2 minus 4 over x n plus 2 did converge to negative 4 as the sequence xn progresses. You understand? So hence, in this case, so hence negative 4 is the limit of the function Okay, so that's actually what it was about. So fx equals x squared minus 4 over x plus 2 as x approaches negative 2. Okay? You understand?
Yeah, but there is a minus missing, I guess, in the first.
Sorry, x equals negative 2. Sorry, yeah, that was a mistake. So if the sequence xn approaches 2, then the function would actually approach 0. So then the limit of the function would be 0 in that case. Okay, you understand? So I don't need to consider the abstract definition, okay, in terms of the limit of the function, guys. All right. Okay, so because I already know what the limit of a sequence is. Okay, it's in the lecture notes. So this is the so-called epsilon delta definition. Okay, but you don't need to consider that. Okay, maybe it's too complicated if you see it for the first time. So basically, I don't want to go into that. It's enough actually that you know what the limit of the sequence is. So by using the limit of the sequence, that we can define. This is also true for, and that is always, of course, that is always true for any sequence. Okay, so as n approaches infinity in this case. Okay, did you get the point what I was talking about? Okay, maybe you didn't consider that to be a certain limit or stuff like that. Now, guys, okay, so in this case we distinguish also between the so-called left-sided limit and the right-sided limit. So the two limits can be different, let's say, if x approaches the function from the left and x approaches the function from the right. Okay, so basically it can be also something else though. Alright, so okay, so that is what we are looking at. Okay, so this will be let's start with the right-sided limit first. Okay, so the right side, this is the next definition. Okay, so that's going to be the next definition. Okay, so and what is a right-sided limit? Okay, so this will be the so-called right-sided limit. So basically what we have is that we make a restriction on it. So for all sequences that approach is actually the function from the left and approach function from the right. Okay, so let's say we have the following. So this will be as follows. So let's say if xn converges to p, okay, then this shall imply that the image or the images of xn will converge to L, okay, but there is a restriction, okay, so the restriction is that xn is always greater than p, okay. So in this case we say that this will be the so-called right-sided limit, okay. I'm going to consider an example for that so you understand this, okay. So for all sequences that approach actually x and that actually approach p, from the right, okay, we find that this is actually the case. So then this will be the right-sided limit of the function, and the left-sided limit, okay, and this is what we call the left-sided limit. Okay, there are different notations for that. So this is the left-sided limit. You will see that is actually different. Okay, so what would be the difference? I mean, if let's say that is true, then this might be also true where xn is not greater than p, okay, but xn is less than p. So if let's say xn approaches p from the left, okay, then the limit of the images shall be equal to L. So then in this case L will be the left-sided limit, okay, so then this will be the left-sided limit. Okay, so here in this case L, okay, so here L is the right-sided limit, and here in the bottom here it will be the left-sided limit. So if let's say xn approaches p, and that implies that the images, okay, of xn approaches L, okay, where actually